So now we're going to get back to it, and we're going to talk about oxygenation. Now, oxygenation is the process of oxygen molecules actually being loaded onto hemoglobin. Okay, this is that piggybacking that we keep talking about. You can't move around, no different than insulin and sugar. Oxygen cannot move around in the bloodstream and get into anywhere. It can move around on its own, but it can't get into anywhere unless it is attached to hemoglobin. Okay? To get across those barriers and those membranes, it has to be attached to hemoglobin. Okay? This is something that has to happen for internal respiration to take place. If you have ventilation but no oxygenation, nothing else matters. Okay? You can ventilate all day. So if you think about it, all three of these phases have to work in conjunction for this to happen. Air has to come in, oxygen has to bind to hemoglobin, hemoglobin has to carry it around the body to the end user, and it has to go into those cells for it to work. Okay? For oxygen to make it to where it needs to be, all of this has to take place. Okay? Just because you're oxygenated does not mean that respiration is going to take place. The cells themselves or the organs have to accept that oxygen. Okay? And just because there's ventilation doesn't mean that oxygenation is going to take place. Air can come in, but the alveoli has to accept it. And one of the instances where we see this, and we'll talk about it more later, is congestive heart failure. Air can get into the lungs, but if there's fluid or pneumonia or if there's fluid in the instance of congestive heart failure, if it's a pneumonia, if it is asthma, any of the major respiratory diseases, there's going to be something there that's going to keep that from happening like it's supposed to. But the biggest one, like I said, is CHF, because fluid is blocking those alveoli and keeping gas exchange from taking place. Okay? So if that's the case, we got to figure out how we can get that fluid out there so we can make the gas exchange happen. All right? Then ultimately we have respiration. Now, again, this is the oxygen getting to the end user and the carbon dioxide exchanging due to diffusion and getting out the body. All right? The actual exchange of carbon dioxide is at the alveolar level, and it happens at each spot along the way. It's no different than, you know, as you travel on the tube in London or you get on the subway in New York. What happens? People get off, people get on. This is exactly what happens at each one of these junctures. So just when you get to the liver doesn't mean every bit of oxygen comes off and every bit of CO2 comes on. No. But every bit of CO2 that's in the liver comes on, but a little bit of oxygen goes in to replace what's moved out. Okay? So just like, think of it like the tube system or like the subway system. All right? Every time something moves, or you get to another stop, a little bit of oxygen goes out, a little bit of carbon dioxide comes in until it gets back to the lungs to be expelled from the body. This is all what's referred to as cellular metabolism, okay, or cellular respiration. This is that metabolism that we talk about, okay. Metabolism means that something's being utilized and converted for something else, okay. Metabolism just means that something's being utilized and converted for something else. So they take energy from the nutrients and from the oxygen through all these chemical processes, and that is your metabolism. This is how that stuff gets used. Okay? So for external respiration, or what's referred to as pulmonary respiration, there's two different parts to this. External happens as air moves into the respiratory system, and this is at the alveolar level. This is carbon dioxide moving out and being breathed out, and oxygen actually moving on to the hemoglobin at the pulmonary capillaries. Okay? So oxygen moves onto the hemoglobin at the pulmonary capillaries and gets ready for transport. Like I said, no different than when you walk into the subway, you go down, you drop your token in, boom, you get onto the train. This is oxygen getting onto the train, carbon dioxide getting off the train. Okay? At this point, then, subway closes, takes a ride. Now, as we take that ride, again, surfactant keeps the alveoli open, making gas exchange possible. Okay? Just like anything else, it has to be in a warm, moist environment in order for this to take place. Alright? So as that happens, it gets to the first organ. Boom. Say it goes from there, stops at the liver. Okay, whichever organ it stops at first along that train ride. Well, what happens? A couple of the riders get off, that's oxygen, and a couple of riders get on, that's carbon dioxide. So oxygen moves off, carbon dioxide moves on, moves to the next stop along the station route. Okay, so if you think about it like MARTA, and you're traveling from 5 Points, and then you hit, East Lake and all the, couple stops along the way until to get to wherever you want to go in the east or west route, what have you. And then ultimately to end up back at the lungs, you're all the way at the end of the line, which I think is Indian Creek, the last line out there in Stone Mountain. You end up all the way out there on the west side, okay? Or in the instance of the subway in New York, you end up out in Long Island somewhere, right? So you take that ride, till you get to the terminal end. All right, then the process turns around and starts again. Okay, once it gets to the lungs, what does it do? Load on more oxygen, take the ride back, right? So it does that continually, just keeps going back and forth, back and forth. Users get on, users get off, and that's what your respiratory cycle is in a kind of an easy nutshell. Okay, but this is the systemic circulation. As you see there, carbon dioxide moves out, oxygen moves in. But if you notice, it's not all of it. It's just a little bit at a time. It's just what that cell needs. Because based on what's going on in your body, in order to maintain, keyword, one of the Pee Wee Playhouse words, makes you yell, homeostasis, whatever the oxygen demand of that cell or that organ at that time, it's going to ask for. Okay? Whatever the oxygen demand of that organ or that cell needs at that given time, it's going to ask for it. Okay, so it may have more at a given time. Say we're in the middle of eating and the stomach needs more, or the intestines need more, or whatever, in order to start making things move. That's going to happen. Say we're working out, the brain and the heart are going to need more, so they're going to ask for more, right? So just depending on what needs what at any given time, it's going to ask for extra nutrients, the brain's going to ask for extra sugars, those sorts of things. So that's what happens during this process. Okay? And the thing we have to remember with respiration is time is brain. This goes back to stroke. Okay? And when we talk about stroke in a couple chapters, we're really going to hone in on that. But remember those numbers I told you. 8 minutes for cardiac death, 12 minutes for brain death. Okay? As it shows here, it shows 10 is when irreversible starts, but actual death of tissue starts at 12. Damage starts at 10. Okay? Irreversible brain damage starts at 10. And this is just kind of a guideline. But what happens is the longer it stays that way, the larger the area of damage. So you have an area of big damage, an area of minor damage, and an area of very minimal damage. And the longer there's no oxygen, the more that area expands. Okay? So some of the factors that will affect this, okay? Well, one, all the cells need a constant supply of oxygen to survive, okay? Just like we need food and water, we can go, 20, 30 days without food, but can we go more than 7 days without water? No, we gotta have it, okay? There has to be an adequate supply of oxygen, there has to be an adequate supply of nutrients, specifically glucose. The body has to have something to burn. If the body doesn't have something to burn, it'll turn to what it already has and start burning your fat. Anybody ever heard of the Atkins diet? Yeah? Well, when you talk about the Atkins diet, that's what your body does. It stops taking in certain carbohydrates and it starts burning what it already has. It's a process known as ketosis. The only problem with that is your body can only do that for so long before it actually makes you sick. Okay? So it'll only work for a while, and that's what's referred to when glucose is converted into energy. That is known as aerobic metabolism. You said it earlier, okay? And we talked about anaerobic metabolism, when the body's oxygen starved and still trying to work. Well, just like I always say, when we do CPR, it is an aerobic workout. The reason it's an aerobic workout is because you got to breathe, okay? Otherwise, you'll be the next victim. So we use aerobic metabolism in an aerobic workout in everything that our body's supposed to do. The longer we're without oxygen, the more anaerobic our metabolism becomes. And again, we can't meet those demands for very long. And what'll start to happen is your body will do something called shunting, where it'll start pulling blood and oxygen from the peripheral, so the hands, the feet, stuff like that, to the core organs. And after a while, it's going to cause you to pass out because your body can only do that for so long. Okay. Some of the things that affect the nervous system, okay, or how it affects the nervous system when we breathe, is those chemoreceptors. Bless you. Those chemoreceptors affect our oxygen, and they look at our oxygen. They look at, bless you, they look at carbon dioxide, they look at hydrogen ions, and they look at the pH of the cerebral spinal fluid, or CSF. Okay. So, in a nutshell, everybody got that? Before I delete it? Or erase it? Yeah?
Yeah.
Okay. Make sure. What it looks at is it looks at O2, CO2, hydrogen ions, and then pH. Okay? And pH of the CSF, okay, is what it's actually looking at. Okay? So it looks at oxygen, carbon dioxide, hydrogen ions, and the partial pressure of hydrogen in the CSF. Okay? So, just so you know, what's our normal oxygen level supposed to be?
21%.
That's what we breathe in, is 21%.
Right.
That's what normal air is. What we actually should have in our blood at any given time is 96 to 100%. Okay? That's what our normal oxygen range is supposed to be. Alright? Our normal CO2, these are the things we look at, is supposed to be 35 to 45 millimeters of mercury. Okay? These are our normals. Okay? Hydrogen ions, we're not going to spend too much time on that, but what we're going to talk about is the pH in our CSF. 7.35 to 7.45. This is what our pH is supposed to be in the CSF and in the blood at any given time. You notice how those numbers look vaguely familiar? It's an easy way to remember that. pH, just remember 7 plus 35 to 45. Right? Easy way to remember that. 96 to 100, 35 to 45 millimeters of mercury, and pH of the CSF and blood are supposed to be 7.35 to 7.45. Those are our normals. Okay? Anything less than this, you're acidic. Anything more than that, you're what's referred to as alkalotic. Or
Now,
you're here to say
and those, when your pH is off,
Yep.
is whenever you could become septic, correct?
Yes.
That's what that's
Yes.
from.
And usually that's because your
Your
acids are off. Yes. That's correct. Okay? But all three of these work in conjunction. Okay? And there's another that we talk about, which is the bicarbonate levels. Okay? And bicarbonate levels are also affected by your breathing. And the normal for bicarbonate levels, which is, I'll write those down too, that's H, oh, that's the one that messed up. HCO3 negative, okay? That's bicarbonate, or bicarb level, okay? Is normal is 22 to 26. That's your normal range for bicarb, okay? 22 to 26. And all of these are part of that respiratory cycle, okay? So your normals for O2 are 96 to 100. Your normals for CO2 are 35 to 45. Your normals for pH of cerebral spinal fluid and blood are 7.35 to 7.45. And your normals for bicarb levels are 22 to 26.
Now with your pH being off, high or whatever.
Yeah.
That's, I mean, I've heard that runs like with gout.
It can.
They'll say your pH. I mean, because I found that out the hard way.
Yeah.
My foot swelled up and I couldn't figure out why.
Yep.
And I went in and they drew blood and they told me my pH level was too high. And
Yes.
And it caused, you know,
And they had to give you fluids, potassium, stuff like that to
Right.
bring it balanced out. Yeah, yeah, and that'll happen. That'll happen because you're being slightly alkalotic is not a bad thing, and that's like the water and stuff that they sell that's like high in pH right now, what have you. So you take your body from being acidic to being slightly alkalotic is actually good for you, but only slightly. Once you move outside, because normally our body lives almost in a state of in a slight state of acidosis. We always are kind of on the acid side. So the water that we drink normally doesn't have a high enough pH to counteract that. So that's why these new things like Essential and things like that have like a pH of 8, 9 or whatever in order to make it a little bit higher, okay? Or to make the body's pH a little bit higher. Okay, so what happens with each of these is, like I said, the body provides feedback from each of these to the respiratory system, okay, that apneustic and pneumotaxic center. Let me write those down for you so you can see how they're spelled and all that good stuff. Okay, so it's the apneustic and pneumotaxic centers, okay? This is where we breathe from. Anybody ever seen the movie The Waterboy? What do they talk about? The what? Where happiness comes from. Not because Alexander kept
Medulla oblongata.
Okay? This is where that is. It's the medulla and the pons. Okay? Remember we talked about head injuries, and we said that if somebody sustains a head injury and they start to herniate, the problem is that it's pressing against that area of the brain that causes all those primal instincts to happen. Causes us to breathe, causes us to not pee ourselves or poop ourselves, all those sorts of things. That's this. That's the very, very base of the brain before you get to the spinal cord. Okay? That's these two areas. The problem is when those are affected, all of your primal body functions are affected. So breathing is one of them. That's why if you have somebody that has a head injury, the first thing you see go is their respiratory. Okay? If they have swelling in that intracranial vault or inside that brain, the first thing you see act up is them breathing funny. Because it's swelling and it's pushing down. And the minute it pushes down, it's pushing against that area. Okay? That's a problem. So we got to fix that quick. And the way we fix that, we're going to talk about it today, is that we bag. But we bag at a very slow rate. We're going to bag about 6 to 8 times a minute. That's it. Because we want them to have oxygen, but we want to decrease that intracranial pressure. So we bag a little bit slower to decrease intracranial pressure. You only bag about 6 to 8 times a minute, normal tidal volume, and you'll see that you'll start to see their breathing begin to return to normal, depending on how bad the herniation is. Okay? But we're going to go into that. And we're actually going to do some hands-on airway stuff today, putting in NPAs, OPAs, that sort of stuff. Okay? So, part of the ventilation process is something called ventilation perfusion mismatch, okay? Or VQ ratio, okay? The Q stands for perfusion. Don't ask. It's just a thing. They talk about airflow, which is actual ventilation, and then they talk about blood flow, which is perfusion. So those two have to meet up, okay? If they don't match, there's not going to be gas exchange. There's going to be a lack of oxygen in the bloodstream. There's going to be circulation issues with carbon dioxide, and there's going to be something called severe hypoxemia. Now, what I'm going to do real quick is I'm going to change to a different slide, and I'm going to show you some VQ mismatch. I'm going to show you a slide on VQ mismatch. Give me just a second. Okay. Okay.